In this video, we'll be learning how to find the domain of a composite function. Now, our starting point will be the generic composite function f of g of x. And now let's say we were to plug some number, some value inside this function, and we'll call this number a. Now when we do this, the first place a goes is inside the inner function g of x. So I'll just write inner here. And so via g of x, a is turned into some new number, g of a. Now already this shows us a couple of things. The number a must be inside the domain of the inner function g of x. So must be in domain of g of x. And also, since this number g of a is produced by the function g of x, g of a is inside the range of the inner function g of x. So inside range of g of x. Okay. Now the next thing that happens is this new number g of a is then turned into another number via the function f of x. And f of x is the outer function of this composite function. And via f of x, g of a is turned into f of g of a. And so, since it's produced by f of x, we can see that the final output must be inside the range of the outer function f of x. Now this highlights a very important thing here. This intermediate value, g of a, since it's going to be plugged inside the function f of x, it must be inside the domain of f of x. So I'll just add this here. Must be inside domain of f of x. And in fact, it's that point, that key point, which will be at the heart of finding a composite function's domain. We'll need to make sure that whatever number we plug inside a composite function, that g of a, or the value of that number, once we throw it inside the inner function, must fall inside the domain of the outer function f of x. Now I know that sounds quite complicated. Let's go right ahead and see how we can do this with a couple of examples. So let's say we're given the following. F of x equals to the square root of x, and g of x equals to x squared plus 1. And we need to find the domain of the composite function f of g of x. Well, to do this, the best way, or the best starting point really is to just look at the functions f and g and to find their domains and their ranges on their own. So ignoring the composite functions altogether for a second, let's just find the domains and ranges of f and g. Well, we know that f of x equals to the square root of x, and the domain of the square root function is domain equals to all real numbers such that they're greater than or equal to 0. In other words, the square root function is defined for numbers greater than or equal to 0. Fine. And we also know that the square root function has range equal to its domain, which is all real numbers such that they're greater than or equal to 0. Now we do the same for the inner function, g of x, and so g of x equals to x squared plus 1, and in this case, the domain, well, the domain is all real numbers. Indeed, there isn't a single number for which we couldn't calculate x squared plus 1. So we write domain equals to all real numbers. And its range, in this case, well, the range is all values greater than, in this case, the vertex. So, in this case, the vertex is at 0, 1, so the range would be equal to all real numbers such that they are greater than or equal to 1. Now, if you're having trouble picturing that range, make a quick sketch of this function's curve. This function's curve would be the parabola with equation y equals to x squared plus 1. And that would look something like this. We'd have a parabola which would go down and back up. Its lowest point would be at 1 on the y-axis. And so we can see that its range are all the values greater than its lowest value, which is 1. Now, to make sure that this composite function is well defined, we need to ask ourselves whether or not there are any values inside the range of the inner function which are outside of the domain of the outer function. So we can see that the domain of the outer function are all real values, all real numbers greater than or equal to 0, and the range of the inner functions are all real numbers greater than or equal to 1. And it quickly becomes quite clear that any number greater than or equal to 1 is also greater than or equal to 0. So in this case, we can just go right ahead and say that the domain of f of g of x equals to the domain of g of x, the inner function. And so we can just go ahead and write that the domain equals to R. Now, let's make sure we've understood what's just happened. Essentially, we've just shown that the domain of the inner function is all real numbers, R. And we checked its range. We saw that its range was all real numbers greater than or equal to 1. And we also saw that the outer function was well defined for all values greater than or equal to 0. And so since the inner function doesn't produce any values that fall outside of the domain of the outer function, this composite function is well defined for all real numbers inside the domain of the inner function. So there was no real work to do here. And we stated that the domain of this composite function was all real numbers. Now let's look at another example. Let's say in this case we're told that, again, f of x equals to the square root of x, and we're told that the inner function g of x equals to 2x minus 4. And again, we're asked for the domain of f of g of x. Well, once more we start by looking at the domain and ranges of each of these two functions. We've already seen that f of x equals to square root of x has domain equal to all real numbers such that they are greater than or equal to 0. We also saw that its range was all real numbers greater than or equal to 0. Okay, and now the inner function, g of x, equals to 2x minus 4. And in this case, it has domain equal to r. Indeed, there isn't a single number we can throw inside g of x for which it won't be defined. So the domain is all real numbers. And the range, in this case, is also r. And we can confirm this just by looking at this function's graph. Y equals to 2x minus 4 is a straight line looking something like this. And it cuts the y-axis at negative 4, and it cuts the x-axis at 2. Now that we've done this, we need to look into whether or not there are any values inside the range of the inner function, which is all real numbers, that fall outside of the domain of the outer function, which is all values greater than or equal to 0. And now we quickly see that there are quite a few values inside the range of the inner function which fall outside of the domain of the outer function. And indeed, just looking at this function's curve, when we look at y equals to 2x minus 4, we can see that this, or the y-coordinates of this line, are only positive for x values greater than 2. So we need to be careful here. We need to make sure that we only consider g of x when it's greater than or equal to 0. And to do this, just to make sure we do it correctly, we're going to solve the inequality g of x greater than or equal to 0 to make sure that the values of g of x fall inside the domain of the outer function f of x. So g of x greater than or equal to 0 leads us to 2x minus 4 greater than or equal to 0. That leads us to 2x greater than or equal to 4, which leads us to x greater than or equal to 2. And there you go. That's the restriction. We need to make sure that x is greater than or equal to 2. So long as we do so, we can be sure that g of x will be greater than or equal to 0, and therefore will be inside the domain of the outer function f of x. So now that we've done this, we can say that domain of f of g of x is all real numbers such that they are greater than or equal to 2. And that's the domain of this composite function. Now, don't hesitate to watch this again a couple of times. This is a very important topic, and we've learned a fair share of things in this video, and I really hope this helps.